All right, we're going to move on to another factor that affects stability of the conjugate base. Okay, now this one is called resonance effect, and I can't stress enough how important the resonance effect is. Drawing a resonance structure we did together since what, chapter 2, we do again in chapter 3, chapter 4, 5, until the entire course. We were still going to do the resonance structure. Move on to organic chemistry 2, you're still going to do the resonance structure. It's really important. Okay, all right, so let's see if you can recognize the resonance here. All right, so what we got, we have perchloric acid, which is the strongest acid here, negative pKa negative 10, chloric acid negative 6, still relatively strong acid. And these two are weak acid. We have chlorous acid and hypochlorous acid. Okay. All right, so how come these two are strong acid, but down here are weak acid? Well, let's draw out their conjugate bases. Okay. Here we go, it's conjugate bases. Now, all of them negative charge on oxygen, negative charge on oxygen, negative charge on oxygen, all of them same thing. All right, the size, electronegativity, everything else the same. But what's the tiebreaker here? Well, the negative charge in this structure right here, okay, we call perchlorate. Right, negative charge on perchlorate doesn't stay on oxygen. It's stabilized or being distributed to 4 oxygen, all of them. Pay the roles here. In the case of chlorate ion, this negative charge being shared by 3 oxygen, and this guy got 2. This guy doesn't have anyone to share with. Okay, the resonance effect come to play out. All right, I'm going to show you here. So perchloric acid, the strongest acid among this acid here, that's the conjugate base, right? Perchlorate. Now you can you see that this is negative charge here is in allylic position, double bond here. The next position, the position next to the double bond, that's an allylic position. You can draw a resonance structure there. Not just one time, you can draw another one to the oxygen on the left. You can do resonance to oxygen at the bottom. So there are 4 resonance forms total. You know? In the case of chloric acid, all right, let's draw out the conjugate base first. You get that? And the same thing, negative charge, a position away from double bond. That's an allylic position. You can do it. Share negative charge with the oxygen at the top, and then you can do on the left as well. So 3 resonance structures. Yeah. And down here, what we got, chlorous acid. All right, make it a conjugate base. Now, this negative charge is shared between 2 oxygen. And the last one, you can get, there's no one to share with it. Negative charge just on that oxygen. Okay. All right. So what's going on here? Look at this structure right here. So this negative charge being shared by 4 oxygen, just like the same thing with the size we talked about earlier. The negative charge spread out in a larger area. Then this negative charge is really happy. They have a large area to run around. Right. This negative charge have a less space, but it's enough. 3 oxygen help each other stabilize the negative charge. For 2 oxygen, not enough now. This guy become a weaker acid. And the last one, this negative charge has no one to share with, to stay on that oxygen. This guy become really weak acid there. Okay, so perchlorate is a more stable conjugate base, and that makes perchloric acid the strongest acid in here. Okay, all right, let's look at right here real quick. Let's see if you recognize the resonance or not. All right, so both of them, we have an alcohol. If you still remember pKa 5, we have carboxylic acid pKa. No, I said it wrong. Alcohol pKa about 16, carboxylic acid pKa about 5. Right? How come though? Let's take a look at the. Let's take a look at their conjugate bases. Right? So first off, the negative charge on oxygen. Size the same, electronegativity the same, but the difference is this guy have resonance. This guy does not, right? You can try to draw resonance. Oh, nope, that's the overoctet carbon in the middle. You can't do that. But you can do this if you recognize the allylic lone pair, right? Here we go. So you get 2 resonance forms. There's no doubt that if you look at this kind of this structure right here, they call electron potential map or something like that, show that the red kind of red, let's see, the red in color, that's where electrons are being shared between 2 oxygen. In the case of ethoxide here, the electron just stay on that oxygen here. You know? And there's no doubt carboxylic acid is a stronger acid than an alcohol. pKa 5, pKa 16. Okay. All right. So if you see allylic lone pair, that's when you can draw a resonance form. So don't forget that. right? So recognize that. All right, let's see what we got here. Try to on your own first and then check in with me. Okay, draw a resonance structure of these two. All right, of the not these two, the conjugate base of these two. Draw out the conjugate base first. All right, you should be able to recognize now that the structure at the top has no resonance structure. Ta-da, that's nothing there. You can't draw that, right? That's over octet this carbon. But down here, that's allylic position, double bond, a position away from double bond. That's an allylic position. You can draw a resonance from there. And this resonance from create another allylic position, double bond here, the position next to it, you can do another one. And now you have another allylic position, double bond here, that's allylic position. You have another one there. That so 4 resonance structures there. There's no doubt that that's why the alcohol. If you still remember a normal pK of alcohol about 16, but this guy is a special alcohol, OH attached to the benzene ring. You still remember that, right? So pK about 10. Okay. All right. Now come down here. Let's see if you recognize the resonance structures. All right. All right. Make all of them draw out the conjugate bases. All right, the top one alkane. This guy never been an acid because this guy really unstable. Nothing stabilizes it. You can't draw a resonance structure there. Doesn't make any sense, right? Over octet carbon in the middle. Down here, alpha proton. This guy is a little acid because their conjugate is conjugate base. It's a little stable. It's being stabilized by the oxygen right here. That's allylic position, right? You can draw the resonance structure. Yep, you got 2 resonance structure there. All right, and down here you get an effect of 2 ketone. Now stabilize this negative charge out. Draw it out on the left side, and you can do on the right side as well. So that's the reason this guy have more stabilized. That's the reason why the diketone right here is more acidic than just regular ketone. So pK 9, pK about 20, and alkane of course nothing stabilizes it, not an acid at all. So pK 50. Okay. All right. Who's the most acidic, H1 or H2? Do you recognize the resonance though? If you're not sure, well, first thing first, draw out the conjugate base of the H1 and H2. Okay. All right. So start with an H1. So there's a conjugate base of H1. Does it have anything stabilize it? Not really. Just negative. Just electronegativity of the nitrogen stabilize the negative charge, but that's it. Okay, if you you cannot draw the resonance, you can draw on the left and the right. I mean, you over octet the carbon around it. All right, let's try on H2. Draw out the resonance structure. Look, not resonance, the conjugate base structure. Look like that. Do you recognize the resonance though? There's a double bond. The negative charge on the position next to the double bond. That's an allylic position. Right? You cannot draw to the right, but you can do from the left side. Around the ring there, you can draw out 3, 1, 2, 3 structure there. I just do the 1 there for you. Okay, so which means that this negative charge is being stabilized not only by the nitrogen, but the whole ring here helps stabilize that negative charge, right? So this negative charge is happier or more stable than the negative charge on the other nitrogen. H2 is more acidic. That's it. That's how we do it. All right, so more resonance from H2. Okay. All right, let's go to the next chapter, next video.